Hello everyone, and welcome. I'm excited to kick off today's presentation on areas related to circles. On this first slide, you'll see the title, Areas Related to Circles. We'll also explore some key concepts related to the areas within circles. In the upcoming slides, we'll cover topics like the area of a circle, sectors, segments, and how these relate to each other. So, let's get started and dive into the fascinating world of circles. Let's take a quick look at the contents of today's presentation. We'll start with circles, covering parts of a circle and how to find their area. Then, we'll explore segments and sectors, understanding what they are and how to calculate their areas and lengths. We'll also look at real-world applications, like the area swept by a clock's minute hand, which ties into measuring angles and sectors. Moving on, we'll discuss important theorems that help us understand these concepts better. We'll also see how to convert units, which is essential when dealing with measurements in different systems. Finally, we'll wrap up with some questions and a summary to reinforce what we've learned. Throughout this presentation, I want you to see how these geometric ideas connect and why they're useful in everyday life and problem solving. Let's take a closer look at circles. Circles are one of the most fundamental shapes in geometry, and they have some fascinating properties. For example, every point along the edge of a circle is equidistant from the center. This distance is called the radius, and it's a key concept when understanding circles. The line that passes through the center and touches the circle at 2 points is called the diameter, which is twice the radius. Circles are everywhere around us, from wheels and clock faces to the shape of planets. They also play a crucial role in various design and engineering applications because of their symmetry and efficiency. When we think about circles in the context of our overall theme, it's about understanding how simple shapes can have complex and useful properties. Recognizing these properties helps us better analyze structures, optimize designs, and appreciate the beauty of geometry in everyday life. Let's take a closer look at area and perimeter. These are two fundamental concepts in geometry that help us understand the size and shape of objects. When we talk about the area, we're referring to the amount of space inside a shape, like how much paint you'd need to cover a surface. Perimeter, on the other hand, is about the distance around the shape, kind of like measuring the length of a fence you need to enclose a yard. Understanding the difference between these two is key because they serve different purposes. Area tells us about the size of a surface, while perimeter relates to the boundary length. Throughout this presentation, you'll see how both concepts are used in real-life situations, from architecture to design. They are essential tools for problem-solving and making informed decisions about space and boundaries. So, keep these ideas in mind as we move forward. It'll help you see their importance everywhere. Let's dive into some key theorems that deepen our understanding of circles. First, the theorem states that the perpendicular from the center of a circle to a chord actually bisects the chord. What this means is that if you draw a line from the center at a right angle to the chord, it will cut the chord exactly in half. Next, the line drawn through the center of a circle to bisect a chord is perpendicular to that chord. So, the same line that bisects the chord at a right angle is always passing through the center, reinforcing the special relationship between the center, the chord, and this perpendicular line. Finally, there's an important relationship involving angles and arcs. The angle subtended by an arc at the center of the circle is double the angle subtended by the same arc at any other point on the remaining part of the circle. This is a fundamental concept that helps us understand how angles relate to arcs across different parts of the circle. These theorems are crucial because they connect various elements within a circle, lines, angles, and arcs, and they serve as the foundation for many geometric proofs and problem-solving strategies we will explore further. Now, let's talk about angles in the same segment. When we have multiple angles sharing the same segment, an interesting property emerges. All those angles are equal. So, if you identify multiple angles within that same segment, you can be confident they measure the same. This is a helpful idea when solving geometric problems because it allows us to set angles equal to each other. Another key point is about angles in a semicircle. Remember that a semicircle is half of a circle, formed by a diameter and the arc. Any angle inscribed in a semicircle meaning, with its vertex on the circle and sides intersecting the circle, will always be a right angle, measuring 90 degrees. This is a very useful fact because it simplifies many problems involving circles and angles. So, to connect this to our overall theme, understanding these properties helps us analyze and solve geometric figures more effectively. Recognizing when angles are equal, or when an angle must be a right angle, saves us time and guides us toward the correct solutions. Let's take a closer look at the parts of a circle. First, we have the minor arc, which is a small segment of the circle's circumference. Correspondingly, the minor segment is the area between this minor arc and the chord connecting its endpoints. The circumference itself is the complete distance around the circle, and the radius is the distance from the center to any point on the circle. When we talk about a minor sector, we're referring to the part of the circle bounded by two radii and the minor arc. Now, moving on, the diameter is a special line that passes through the center and touches 2 points on the circle, effectively dividing it into 2 equal halves. Sometimes, we encounter a major segment, which is larger than the minor segment, formed by a major arc. This is an arc measuring more than 180 degrees. Similarly, a major sector is a larger slice of the circle, bounded by a major arc and radii. And finally, a very important concept to understand is the tangent. A tangent is a line drawn at right angles to the radius at the point where it touches the circle's circumference. This line just grazes the circle at that point without cutting through it. Recognizing these parts helps us understand the geometry and relationships within a circle, which is fundamental to many areas in mathematics and beyond. Let's talk about what a sector actually is. Have you ever had a slice of pie or a piece of pizza? Well, those are perfect real-life examples of a sector of a circle. So, a sector is basically a wedge-shaped part of a circle. Imagine taking a slice out of a pizza. That's a sector. It's made from 2 radii, which are like the lines that come out from the center of the circle to the edge. The plural of radius is radii, by the way. Think of a radius as the line from the crust of the pizza straight to the middle. That's pretty much what a radius is. So, understanding sectors helps us see how parts of circles are divided, which is useful in many real-world situations, and of course, in understanding more about circles and their properties. Let's talk about what a segment actually is. A segment is a part of a circle that is enclosed by a chord and the corresponding arc. Think of it like slicing a pizza. Each slice is a segment. For example, if you cut the pizza in half, each half is a segment called a semicircle, which is actually half of the entire circle. Now, because a circle's circumference has infinitely many points, there are countless ways to draw chords and create different segments. This means there's a lot of variety in how segments can look and what parts of the circle they can cover. Understanding segments helps us see how different parts of a circle relate to each other, which is a key idea in geometry and in understanding shapes around us. Let's talk about the area of a sector. A sector is like a slice of a circle, defined by 2 radius lines and the arc between them. To find the area of this sector, we need to understand how much of the circle it covers. The key idea is that the area of a sector depends on the central angle that it subtends at the center of the circle. If the angle is in degrees, we take the ratio of that angle to 360 degrees, which is the whole circle, and multiply it by the total area of the circle. So the formula becomes the ratio of the angle over 360 times pi times the radius squared. This way, if the angle is small, the sector's area is small, and if it's larger, the area increases proportionally. Remember, this concept ties into our overall theme of understanding how parts relate to the whole in geometry, especially when dealing with circles and their segments. Now, let's explore the area of a segment within a circle. The key idea here is that the area of a segment is found by taking the area of the sector that the segment subtends and then subtracting the area of the triangle formed by the 2 radii and the chord. Essentially, this means that if you imagine the sector, which is like a slice of the circle, and then remove the triangular portion at the center, what remains is the segment. This concept is important because it allows us to calculate the area of any segment by breaking it down into more manageable parts, the sector and the triangle. Remember, understanding this relationship helps us analyze parts of circles more precisely, which is a recurring theme in our study of circular geometry. Let's talk about the length of an arc of a sector in a circle. Now, if you have a circle with a radius r and a sector with an angle theta, measured in degrees, there's a specific way to find the length of that arc. The key idea here is that the arc length depends on both the angle and the radius. To calculate it, we take the fraction of the circle that the sector represents, which is theta divided by 360 degrees, since a full circle is 360 degrees. Then, we multiply that fraction by the total circumference of the circle, which is 2 pi. So the formula becomes theta over 360 times 2 pi. This gives us a straightforward way to find the arc length based on the radius and the angle, and it's a great example of how geometry connects angles and distances in circles, tying back to our overall theme of understanding the properties of circular figures. Let's talk about the distance traveled in one revolution of a wheel. The key idea here is that the distance covered in one full turn is equal to the wheel's circumference. Remember, the circumference is the distance around the wheel. So, if we think about multiple revolutions, the total distance traveled is simply the number of revolutions times the circumference. We can write that as n times c, where n is the number of revolutions and c is the circumference. Now, connecting this to motion, we know that distance is also equal to speed multiplied by time. So, putting it all together, we get the equation n times c equals speed times time. This relationship helps us understand how rotation, distance, and motion are all interconnected, which is very useful in analyzing how objects move over a certain period. Now, we've reached the questions slide. This is your opportunity to ask anything that's been on your mind or to clarify any points we've discussed. I want to emphasize that no question is too small or too big. Your curiosity is what drives better understanding. Remember, the key points we've covered highlight the importance of clear communication, strategic planning, and continuous improvement. These ideas are central to the overall theme of our presentation, which is about empowering effective decision-making. So, please feel free to share your thoughts or ask for further explanation. I look forward to our discussion. All right, let's take a look at this problem. We are given that the diameter of a semicircular protractor is 14 centimeters. Our goal here is to find its perimeter. Now, before we jump into calculations, it's important to recall what a semicircular protractor looks like and what its key measurements are. The diameter, which in this case is 14 centimeters, is the straight edge of the semicircle. To find the perimeter, we need to consider both the curved part of the semicircle and this straight edge. The curved part is actually half the circumference of a full circle. So first, we'll calculate the circumference of the full circle and then take half of it. Remember, the circumference of a full circle is 2 times pi times the radius. Since the diameter is 14 centimeters, the radius will be half of that, which is 7 centimeters. So the full circumference equals 2 times pi times 7. Once we find that, we'll divide by 2 to get the length of the curved part of our semicircle. Finally, to get the total perimeter of the semicircular protractor, we'll add the straight edge, which is the diameter, to this curved length. This approach allows us to connect the concepts of diameter, radius, circumference, and perimeter all together. Now, let's proceed step by step with the calculations to find the perimeter. Let's take a closer look at this problem. We start with a square that measures 4 centimeters on each side, and our goal is to find the area of the remaining portion after certain shapes are cut out. First, note that from each corner of the square, a quadrant of a circle with a radius of 1 centimeter is removed. These quadrants are quarter circles that fit neatly into the corners. Next, we also cut out a full circle with a diameter of 2 centimeters, which means its radius is 1 centimeter as well. Now, the key idea here is to figure out the total area removed from the square. We do this by adding up the areas of all the cut-out shapes, those 4 quadrants and the circle. Since a quadrant is just a quarter of a circle, the total area of all 4 quadrants combined is equivalent to 1 full circle of radius 1 centimeter. Therefore, the total cut-out area from the quadrants is just the area of 1 circle with radius 1 centimeter, which is pi times 1 squared. Similarly, the circle we cut out has the same radius, so its area is also pi times 1 squared. Putting it all together, the area of the remaining part of the square equals the total area of the square minus the sum of these cut-out areas. In the formula, that's the area of the square minus 4 times the area of a quadrant plus the area of the circle. By understanding this breakdown, we see how the geometric shapes relate and how their areas are combined to find the leftover space. Let's take a closer look at this figure. We have a square OABC inscribed inside a quarter circle, or quadrant, OPBQ. Our goal here is to find the area of the shaded region, which is the part of the circle outside the square. First, notice that the side OA of the square is given as 20 centimeters. Using the Pythagorean theorem, we can find the length of the diagonal ob, which will turn out to be the radius of the circle. Applying Pythagoras, BO squared equals OA squared plus OC squared. Since OA and OC are both 20 centimeters, BO squared equals 20 squared plus 20 squared, which is 400 plus 400, giving us 800. Taking the square root, BO equals 20 times the square root of 2 centimeters, which simplifies to approximately 20 times 1.414, or roughly 28.28 centimeters. This BO length is actually the radius of our circle. Next, to find the area of the quarter circle, we use the formula for the area of a circle, pi r squared, and then take a quarter of that since it's a quadrant. So the area of the quadrant is 1/4 of pi times the radius squared. Substituting the radius, we get a quarter times 3.14 times 20 square root 2 squared. When we square 20 square root 2, it becomes 20 squared times 2, which is 400 times 2, giving us 800. So the area is a quarter times 3.14 times 800, which results in approximately 628 square centimeters. Now let's find the area of the square itself. Since each side is 20 centimeters, the area is side squared, so 20 squared equals 400 square centimeters. Finally, to find the shaded region, we subtract the area of the square from the area of the quarter circle. That is 628 minus 400, giving us 228 square centimeters. And there we have it. The area of the shaded region is 228 square centimeters. This process nicely illustrates how geometric concepts like the Pythagorean theorem and area calculations work together to solve real-world problems. Now let's look at this problem involving a rectangle and a semicircle. The paper is in the shape of a rectangle named ABCD, where the length of side OB is 18 centimeters and the length of side BC is 14 centimeters. These measurements give us a clear idea of the rectangle's dimensions. The interesting part here is that a semicircle is cut off, using BC as its diameter. This means the semicircle's diameter is exactly the length of BC, which is 14 centimeters. This is a crucial point because it helps us determine the radius of the semicircle, which is half of the diameter, so 7 centimeters. Our goal is to find the area of the remaining portion of the paper after the semicircle is cut out. To do this, we'll first find the area of the entire rectangle, then subtract the area of the semicircle that was removed. This problem nicely combines basic geometric shapes, rectangles and semicircles, and demonstrates how to handle composite figures. It's a good example of applying our understanding of areas and the relationships between different shapes. So let's proceed step by step to solve it. All right, let's take a closer look at this note. The minute hand of a clock completes a full rotation in 60 minutes, which is exactly 1 hour. Now, since a full rotation is 360 degrees, we can see how much the minute hand moves in 1 minute. If 60 minutes equal 360 degrees, then dividing 360 by 60 gives us 6 degrees per minute. So every single minute, the minute hand moves 6 degrees along the clock face. This is a key concept because it helps us understand how the movement of the minute hand relates to time, and it's fundamental when we're analyzing clock angles or solving related problems. Remember, this gradual movement is what keeps the clock ticking accurately and allows us to measure elapsed time precisely. Now, let's look at a practical example involving the minute hand of a clock. The length of the minute hand is given as 5 centimeters. Our goal is to find the area swept by the minute hand between 6:05 a.m. and 6:40 a.m. To do this, we need to understand that the minute hand moves along a circular path, and the area it sweeps out is basically a sector of a circle. Since the minute hand completes a full circle every 60 minutes, we can determine the angle it moves through during our specific time interval. From 6:05 to 6:40, that's a 35-minute period, meaning the minute hand moves through a certain fraction of the full circle. By calculating that fraction, and then applying the formula for the area of a sector, which involves the radius and the angle, we can find the total area swept. This example beautifully illustrates how we can connect concepts of circular motion and geometry to real-world scenarios, reinforcing the overall theme of understanding how mathematical principles apply to everyday objects like clocks. Now, let's look at the conversions of units, which are fundamental when working with measurements. First, we see that 1 square centimeter equals 10 millimeters times 10 millimeters, which gives us a total of 100 square millimeters. This shows how we can break down larger units into smaller, more precise units. Next, moving to square meters, 1 square meter is equal to 100 centimeters times 100 centimeters, resulting in 10,000 square centimeters. This is a crucial conversion because it helps us understand how larger areas relate to smaller, more manageable units. And then, we also see that 1 square meter equals 1,000 millimeters times 1,000 millimeters, which totals 1 million square millimeters. Recognizing these conversions is essential, especially when dealing with different measurement systems or scales in various applications. Throughout our discussion, connecting these conversions helps reinforce the importance of understanding how units relate to each other, making our measurements more accurate and versatile in real-world situations. Let's wrap up with a quick summary of the key concepts we've covered. First, the area of a circle is given by pi 2, which is fundamental to understanding many properties of circles. When it comes to arcs of a circle, the length of an arc of a sector with radius r and an angle theta measured in degrees is calculated by taking theta divided by 360, then multiplying that by the full circumference, which is 2 pi. Speaking of the full circle, its circumference is simply 2 pi. Now, when we look at a sector, its area is determined by taking the fraction theta divided by 360 and multiplying that by the total area of the circle, pi 2. This helps us understand how much of the circle's area a sector represents. Lastly, the area of a segment of a circle is a bit more involved. It's the area of the corresponding sector minus the area of the triangle formed by the radius lines and the chord. These formulas and concepts are crucial because they connect the geometry of circles to various real-world applications, from engineering to design. Remember, understanding these relationships helps us analyze and solve problems involving parts of circles with confidence.